From where we left off last time, here we are going into some kind of really physics, I guess, not so much mathematics, but hopefully through this physics problem, we bring up some very important mathematics in differential geometry that is applicable to all kinds of so-called gauge field theories. So we started off with dealing with this problem of description of how a charge interacts with an electromagnetic field. Treating the charge quantum mechanically, but treating the electromagnetic field classically. In other words, you don't quantize the EM field, you only quantize the electron, so to speak. And so we do it by what Dirac termed the so-called minimal coupling, and that is to replace the canonical momentum in a field-free Hamiltonian by the momentum minus E over C times A, where A is the vector potential, so to speak, which is defined in its relationship to the magnetic field B, so that B is equal to the curl of A. And we are dealing with a situation where we treat the radiation part of the field and the electrostatic part separately, so that right there we break the so-called relativistic invariance, so that we are talking about a non-relativistic wave equation in here. That is the Schrödinger equation. And the Schrödinger equation, if you do that, and then if you replace P here by h bar over I, the gradient, right? This is how you do it in doing the wave mechanics in a Schrödinger picture. And then the relativistic wave equation becomes something like this. I'm sorry, the non-relativistic wave equation becomes something like this. IE over h bar C A mu squared plus E phi, where phi is the electrostatic potential, this differential operator operating on psi, which is the wave function of the electron. M, of course, is mass of the electron, and so on and so forth. And this is the time-dependent Schrödinger equation, so to speak. Okay? It's ugly in the sense that it is not Lorentz invariant, so that's not good about it. But since we are not dealing with everything relativistically, so this is what we usually do in low energy physics, where you don't have to quantize everything, where low energy means things are not created and destroyed and so on and so forth. There's not enough energy to do so, so that you stay with a non-relativistic picture. And now this mu in here in this particular case only goes from 1 to 3, the spatial component, so to speak. Okay? And so this is the square of a differential operator. And we remarked last time that this differential operator itself, we can write as big D mu, is in fact what is referred to as the covariant derivative in differential geometry. This is the covariant derivative, okay? Not only the partial derivative with respect to spatial coordinates, but with what is called a connection attached to it, A mu being the connection. I'll explain why it is called. I think I started to explain that a little bit last time, okay? But let me just give you a review of it. And so this is the important thing in here. It's called a covariant derivative. Actually, before I discuss this thing in any more generality, I want to demonstrate one thing, namely that even though this Schrödinger equation is not relativistically invariant, there is one very important symmetry to it, and that is the gauge invariance. Okay? This equation not Lorentz invariant. but is gauge invariant. Now, what do I mean by gauge invariance here? Let me explain this. Try to explain this very carefully. This is a very central and important concept in physics. What is meant by gauge in this particular case? What it means is this, at this level. Let's not, again, get into generalities yet, although I discussed this in my classical mechanics course. But let's discuss things with respect to this particular example first, okay? You see, from the very way that the vector potential is related to the magnetic field, you see that all kinds of different vector potentials will give the same magnetic field, okay? Provided, supposing you do something like this, right? You make a replacement, A mu going to A mu plus the gradient of some function. Lambda x. Again, x is some spatial position, okay? Supposing everywhere you see an A, you replace it by A plus the gradient of some function. Then you know, of course, that since the curl of a gradient is equal to 0, right? So if you take the curl of this thing in here, the curl of this part is equal to 0 because the curl of gradient is always equal to 0. So this new vector potential will produce the same magnetic field as this old vector potential, okay? So vector potentials classically are not defined in relation to exactly in relation to the field quantity, and okay, and so that led people to choose the term the choice of gauge. When you choose one particular function, you are said to have picked a particular gauge. But the point is that all kinds of different gauges lead to the same magnetic field. Okay? So one would expect that in classical physics, magnetic field is a force, okay? And since charges only respond to forces, one would expect that the gauge is not important. It's something that's quite arbitrary because all different sorts of gauges lead to the same force. And so there was kind of a prejudice against this A quantity, even though it appears very important because when you write the Maxwell's equations in terms of the A's rather than the E and B fields, it is the A fields that appear within what's called a wave equation in physics, okay? But then, since all kinds of different gauges for a particular for a vector potential lead to the same magnetic field, it's as if that gauge is quite arbitrary. And in fact, you know, in the old physics literature, people talk about a choice of different gauges in different problems, depending on convenience and depending on exactly what you want to do. There are these different things called Coulomb gauges. There are these things called Lorentz gauges, plus many other kinds of gauges, and so on and so forth. Yeah.
Coulomb gauge where the divergence of that is?
Yeah, Coulomb gauge is where you define A such that its divergence is equal to 0. That's one particular choice of gauge, one class of gauge, as a matter of fact. But then there are many others also, okay? Okay, but let's not focus our attention on the specific different gauges which are convenient for different kinds of problems. Those kinds of discussions occur sometimes in some electrodynamics courses. We're not here to worry about the sort of like the comparative advantages of the various kinds of gauges at this point. What we would like to see here is to recognize this fact that the A is not determined as far as if you only want the magnetic field, okay? It's only determined up to a gauge, okay? Now, it so turns out that since the A is used in a Schrödinger equation, then the question becomes, what happens to the Schrödinger equation if I choose a different gauge in here? Apparently, if you choose a different gauge in here, which is different from some original one, then the psi that was a solution that is relevant for the original A field will no longer be the solution for the new gauge. So there's something funny going on, okay? Classically, the electron couldn't care less which gauge you are using, because the electron only sees the magnetic field, right? Because classically, you remember this, the magnetic force is something like E over C V cross B, okay? So an electron traveling with some velocity v classically only sees the B field. All right? But since different gauges of A lead to the same B field, a classical electron couldn't care less what different gauges you're using. But quantum mechanically, it seems that it does, because a wave function that is a solution for a particular gauge suddenly would no longer be a good solution for the new gauge. So what's going on? Okay, and that's the first problem that comes to mind. All right, so that already says that there's something radically different between the quantum mechanical description of the motion of an electron and the classical description of the motion of an electron, when that electron is subjected to an electromagnetic force. Okay? So the way to save this would be to do something like this. So if I choose a different gauge so that this A becomes different, then correspondingly, I have to do something else to the wave function in order for the entire Schrödinger equation to remain invariant, so to speak. We would like the gauge transformation to involve not only the vector potential, but also a wave function, but also a gauge change of the wave function, so that the entire Schrödinger equation has the same form under a so-called gauge transformation when you go from one gauge of the A field to another. Okay? And the answer is that the corresponding wave function would have to go over to something like this, to something new, which is psi x times an exponential factor I e over h bar c, this lambda in here. So these gauge changes go hand in hand in the quantum mechanical context, so to speak. Not only do you have to change, when you introduce a gauge change on the vector potential, this is not the only change you need to bring about. You need to introduce a corresponding change in the wave function also, so that your Schrödinger equation becomes invariant. Okay, now let me show you why it is that you need to introduce this this change in the wave function also. That's a phase shift. That's a phase shift. Yeah, but it means something very interesting. Okay, it's not just a trivial change, in other words, because it's non-integrable, as we'll see. Okay. Yes, in fact, this thing is called a geometric phase. It's some special kind of geometric phase, which can be discussed under much, much more general settings. Okay. So let's say this is a new vector potential, a mu x going to a prime mu x, which is supposed to be equal to a mu x plus the gradient of some function, and then psi x going into some psi prime of x, which is equal to the O psi x wave function multiplied by the exponential of some phase in it. The phase depends on the on this factor lambda that we have introduced into the phase change, gauge change rather, of the vector potential. Okay. Now let's make use of this notation, right? Write the. So we're going to try to see. Now this involves two powers of this. The Schrödinger equation involves two powers of this covariant derivative, right? Because there's a square over there. But let's look at what happens to one power first. Okay. So under a gauge change, this is going to appear as d prime mu psi prime, right? Because under gauge change, the covariant derivative changes also to something involving the new vector potential. Okay. So what we want to see is to see how d prime psi prime, big D prime psi prime is related to the old d prime psi prime. In other words, we're trying to see how the covariant derivative changes under gauge transformation. Okay, and this is very easy to figure out. If you make the associated, the corresponding wave function gauge change. So let's work this out. So this is equal to, let's write it out now, right? So d prime mu would be equal to d mu minus IE over h bar c. Here we are using the new a, so it would be a mu plus d mu lambda. That's a new guy, right? Everything operating on psi prime, but psi prime, the two things in here, right? First exponential plus IE over h bar c lambda x times psi, like that. Okay? Well, let's just turn to crunch it out, so to speak. Okay? So it is equal to, now let's use this d. Now this partial derivative in here, you see, acts on the product of two things. So it therefore you have to use the product rule to differentiate that, which is quite simple actually. So the first term is, let me just differentiate the exponential first. So I have IE h bar c e to the IE over h bar c lambda. Let me write it like that. By the chain rule, then I have to differentiate the lambda, right? Like so. And then times the psi itself, plus, this time I'm differentiating just the psi. So I have e to the IE over h bar c lambda d mu psi. All right? So that takes care of this partial derivative acting on this product in here. And then I have these two other things in here, okay? And then for this a mu term, I just have, let's just write this. Let's just write this second term first, okay? So minus IE over h bar c e to the IE lambda over h bar c times gradient of lambda times psi. And then finally, I have the a mu just multiplied by that. So it's minus, there's a minus sign up front. It's minus IE over h bar c e to the IE lambda over h bar c a mu psi. Okay, that's it, right? Does everybody agree? That's it. The first two terms come from this partial derivative acting on this products. The third and fourth terms come from these two guys multiplied by this. But something very nice happens now. The second and third term cancels out. No, sorry, the first and third term cancels out. Is that right? Yeah, the first and third term cancels out. Minus and plus in here like that. Okay? So leaving only these two terms. Which is simply, so this term cancels with this term, because one is a plus and the other one is a minus. Leaving only e to the IE h bar c lambda multiplied by d mu minus IE over h bar c times a mu, all acting on psi. Okay? That's the second and fourth terms in here. But this is the original d mu psi. All that much is original d mu psi. So you have the interesting fact that d prime mu psi prime is equal to e to the IE h bar c lambda x d mu psi. Under a gauge transformation, the covariant derivative changes in this manner. It just makes the original thing acquire a phase factor. Okay? And you see, here comes the reason why we have introduced this gauge transformation, the associated gauge transformation, so to speak, into the wave function. So as to make sure that that first and third term cancels out, so we have this kind of relationship. Now, let's see what then happens to the second covariant derivative, because it is the second covariant derivative that we want in here, in the original Schrödinger equation. Okay? I'm going to erase all that stuff, all right? It's just very straightforward anyway. You can go home and verify that. It's in your book. So what we want to see now is how the second covariant derivative changes under a gauge change. This then becomes d prime mu square psi prime. Under a gauge change, it would be like this, right? So this is like d prime mu psi prime. Okay? Now, I'm going to make use of this result, right? D prime mu of some kind of wave function in the other gauge. Let's treat this thing, this whole thing, as under the d mu prime in here. That is just simply e to the IE h bar c lambda x multiplied by what? d mu psi, right? See what's happening in here? You treat this whole thing as some psi prime in here, okay? Right? In other words, this is the unprimed one quantity. This is unprimed quantity. This is a prime quantity, whatever it is. So, like that. Okay. When you act on this whole thing once by the covariant derivative in the new gauge, it turns it into this phase factor times the corresponding quantity in the unprimed gauge in here, like that. But this is just actually the original second covariant derivative, right? So you'll have this is equal to IE over h bar c lambda d mu squared psi, like that. In other words, I know precisely how to make a gauge change in this equation in here, because all I have to worry about is this one. Okay? So then, let's see what the new Schrödinger equation looks like in the new gauge. So it would look like minus h bar squared over 2m d prime mu squared. In the new gauge, this would be d prime mu squared. Now, I assume that, now this is something not entirely correct, but non-relativistically, this is okay. I kind of decouple the Coulomb electrostatic potential from the vector potential, okay? So that even though relativistically, because this phi is like the fourth component of a 4-vector field, non-relativistically, I assume that this transforms like a scalar, okay? When a gauge transformation happens, so that the phi itself here doesn't change. See what I'm doing in here? So the new equation would be plus the same E phi acting on psi prime, which I know now, square, right? It's the new equation would involve prime quantities and square, which I know now I can write that in terms of that equation, okay? The second covariant derivative, this guy, is just equal to that same exponential function times the old second covariant derivative. Is equal to e to the I e h bar c lambda multiplied by the old second derivative, let's say yeah, I think this is fine. D mu squared times, no, I think I better be careful in here. Yeah, let me be careful. This is this squared. Oh, sorry, the square is not here. There's no square. There's no square in the E phi. I'm sorry. There's no square in the E phi. Okay, the square is just in the covariant derivative. All right. I'm sorry about that. Okay. So now by this equation, that equal to that, the new d prime square psi prime is equal, acting on psi prime, is equal to that exponential factor acting on this, the old psi, plus E phi times the new psi, which is E I E h bar c lambda times psi, is supposed to be equal to I h bar d dt of the new psi, which is e to the I e h bar c lambda times psi. Okay? Like so. Now, okay. Wait. I made a mistake in my argument in here. Let's just work with the left-hand side first, okay? Just work with the left-hand side. Forget about the right-hand side, okay? So the left-hand side in the new gauge would be equal to that. The left-hand side in the new gauge would be equal to that. Up to here, no problem, right? And obviously, this is equal to e to the I. I can factor out this exponential factor. And then I have minus h bar square over 2m d mu square plus e phi acting on the old psi, like that, okay? But according to the old Schrödinger equation, this part in here is equal to what? Is equal to I h bar d psi dt, according to the old Schrödinger equation, okay? So the whole thing must be equal to e to the I e h bar c lambda x times, let me put the I h bar up front, d psi dt. But here's the thing. The right-hand side is a partial derivative with respect to t, but here the lambda doesn't depend on t. Okay? The lambda is just a function of spatial coordinates. So I can move this exponential factor inside of the derivative sign. So I have I h bar d dt of e to the I e h bar c lambda x psi x, which of course is equal to what? Psi prime. So now look at what I have achieved. I have demonstrated to you that the new Schrödinger equation reads like this. This left-hand side, string it along all the way to the right-hand side, is equal to, but let me just write the right-hand side over here, right? The far right-hand side is equal to I h bar d psi prime dt. Okay? So what does that tell you? The Schrödinger equation appears in exactly the same form in the new gauge. This is what we mean when we say that the Schrödinger equation is gauge invariant. It appears exactly in the same form in any gauge whatsoever. Okay? So if you start off with some A and then change it to another gauge which involves a lambda function, the Schrödinger equation in the new gauge automatically looks exactly the same as the old Schrödinger equation, no matter in what gauge. So this is what is referred to as the gauge invariance of this particular Schrödinger equation. So there's gauge invariance means symmetry, right? So there's symmetry in there somewhere. Later on, I'm going to explain to you what we mean by what kind of symmetry we're talking about. Yeah.
Sorry to ask you to make you repeat yourself, but
That's
after
okay.
the result over on the because it's blocked from monitor, you have
Oh.
of the psi prime. Where did you go after that?
Oh, that's it.
Can I do that?
That's it. I just wrote it there. I just wrote that result over there.
Oh, okay. Oh, I see.
Okay.
Oh, I see.
I just wrote that result here.
Yeah.
I
And
wrote that
this-
underneath that solid line over there.
I
That's
see.
all.
Thank
So
you.
what I've proved is this equation. Starting with the old Schrödinger equation, I have proved this new Schrödinger equation. Okay? Which looks exactly the same as the old Schrödinger equation, but in the new gauge. Okay? That's what we mean again when we say that the Schrödinger equation is gauge invariant. But it is not Lorentz invariant. That's quite obvious, because the time and space coordinates are not treated on an equivalent footing, so to speak. There's a first derivative in t, but a second derivative in the spatial coordinates. Okay? Patently, manifestly, relativistically non-invariant. Okay? That's why it's ugly in a certain sense. Because relativistic invariance, because the Maxwell's equations themselves are relativistically invariant. Okay? And in order to highlight that point before I go on, let me just bring you back to all this stuff about the relativistic or Lorentz invariance of the Maxwell's equations themselves. Okay, see what that means.
Are the Maxwell equations gauge invariant also?
Maxwell's equations are gauge invariant. Maxwell's equations. Well, you cannot use that language in in the classical equations, the Maxwell's equations. Yeah, you can say so. You can say so in a certain, which does not involve the fibers, okay, but it does involve the connections and so on. Well, let's try to clarify that. Okay, let's try to clarify that. I think the answer is yes. I think the answer is yes. Yeah, because the after you quantize, it becomes the Yang-Mills equations. Those are gauge invariant also. Okay. So in classical electrodynamics, you have the E, B, okay, and B is related to A by B is del cross A, and E is related to actually. Sorry, if I remember, this is something like that. Okay, something like that. You remember those equations? Okay, where phi is the electrostatic potential, and these equations are ugly because they don't look the same. Okay, why is there some time derivative, and the space derivatives and the time derivatives do not look like each other, so to speak. Okay, in the two equations. But when you try to cast everything in terms of relativistic language, you see the Lorentz invariance appears quite explicitly. If you do something like that, if you introduce a electromagnetic field strength, F mu nu, it's a second rank covariant tensor. That's related to the A now, A mu. It's like a 4. Let me look at this first. Contravariant first. A mu is like A0, A. A0 is like the time component, which in fact is the scalar potential. Okay, scalar potential is the time component of the 4 vector potential, so to speak, whereas the spatial components of this 4 potential are just this guy, the ordinary vector potential like that. Okay, and if you define F mu nu as d mu A nu minus d nu A mu, then you see that the E and B fields are just the six independent elements of this 4 by 4 antisymmetric matrix. Defined like this guy is clearly antisymmetric. F mu nu is equal to minus F mu nu. Okay, clearly antisymmetric. So in this matrix, the diagonal elements would be equal to 0, all of them. And then it's easy to do the partial derivatives. Remember, d mu is just defined to be d dx mu. Okay, it's just like a partial derivative like that. It changes like a tensor. That's why we use this notation in here. Okay, under a change of coordinates, it changes like a tensor. It transforms like a tensor. Oh, but there's a subtle difference in here. The original quantities are the so-called contravariant, okay, vector. But here, apparently, it's lower index. And here's a reason why we have to distinguish between the upper and lower index. When you use a metric that's other than Euclidean, we use the Minkowski metric. And the way one way to introduce this is, I think that's the way we introduced it in our last chapter, right? This is a Minkowski metric, like so. And if you want to lower an index, you have to do something like A mu is equal to eta mu nu, A nu, sum over nu, okay? Sum over nu like that, all right? So you see that if A upper mu is this, then A lower mu would be equal to minus phi A, like that. The spatial components are not changed. Okay, that's a difference in sign. That's important. Okay. And so now, if you use this equation in here for the A lower mu's, and then proceed to do all the derivatives like this. For example, you can calculate F. Here's F. This is F01, right? So F01 would be D0 A1 minus D1 A0, okay? D0 is like a DDT of A1 component, okay? D1 is what? DDX of A0, but A0 is like phi, minus phi, like so. Okay? Because A lower mu is minus phi in here, like that. Okay? And so this is what? This is precisely, so then F01 is like the first component or minus the first component of this vector. Okay? So F01, this very quantity that I've written down in here, is like the first component of this vector in here. So that must be minus E1. Okay? That must be minus E1. I hope I've done that correctly. And similarly, if you carry out all the other derivatives, you see that this is minus E2, and this is minus E3. And then this is, you find that the curl gives, this is B3, this is minus B2, and then this is E1. Like all of them obtained by using this formula in here. Okay? And so you see the 6 components of the of this antisymmetric tensor. But the 3 components of E and 3 components of B. But the E and B are not naturally separated from each other, because if you do a Lorentz transformation on this second rank tensor, all the E's and B's would be mixed up. So if in one Lorentz frame there's an electric field and no magnetic field, in another Lorentz frame there may suddenly be both an electric field and a magnetic field. Einstein was the first one to show this. Yes?
Why did you put a lower index on
the way it's defined, this is a lower rank tensor in here, lower index.
I mean,
Lower.
matrix for E1.
Oh, it doesn't really matter. I mean, okay. The first component of electric field, second component of electric field, third component of electric field, okay? Well, would you rather deal with this or deal with this? Okay? Under a Lorentz transformation. Under a Lorentz transformation, would you rather deal with this or deal with this? Under a Lorentz transformation, this you can do it. I mean, you can, under a Lorentz boost, for example, you can do it, okay? But this is staring you in the face. This transforms relativistically as a Lorentz tensor, okay, rank 2 tensor, okay? So that you can use immediately those the Lorentz transformation elements, the ones that we mentioned in the last chapter, to calculate the new f prime mu nu in a different Lorentz frame, for example. Okay, which it may be spatially rotated, boosted along a certain direction, and so on and so forth. Okay. The physical lesson is that electric and magnetic fields are not naturally different things. They are just part and parcel of this f mu nu, which that's why that's called a field tensor. Okay. They are naturally mixed in together. That's the supreme achievement of Maxwell. He showed that the electric field and the magnetic fields could be unified in a single setting. Although he wrote his equations in an ugly fashion, which is not manifestly Lorentz invariant, but they are, okay, if you cast it in terms of these relativistic quantities in here. Okay? Now, let me show you that why it is that it's quite clear that. Now, let me extend this gauge transformation to all 4 components instead of just the first, the 3 spatial ones. Okay. Clearly, you can write the 4 vector gauge transformation like this also, where mu can now be 0, 1, 2, and 3. Okay, as opposed to just 1, 2, 3 before. If I do a gauge transformation on A, let's see what changes in here. Okay, what is f prime mu nu, for example? F prime mu nu would then be equal to d mu A prime nu minus d nu A prime mu, like so. Okay? But if you replace this by this formula, d mu A prime mu is A mu plus d, well, this is mu, d mu lambda minus d nu A mu plus d mu lambda. Clearly, these 2 terms cancel out. D mu lambda is the same as d nu lambda because of the interchanging, the commutation of the partial derivatives themselves. And one is a plus, the other one is a minus. So it's cooked up like that, okay? So that the new f mu nu, f prime mu nu, is just equal to the old f mu nu. This is precisely what we learn when we say that you introduce a gauge transformation, you don't change the field. You introduce a gauge transformation, you don't change your field, okay? So classically, the field strengths don't change. But you see quantum mechanically, because of the way that these phase factors occurs in the solution of the Schrödinger equation, it is in fact the A's that are more important than the B's, so to speak. Okay? Now we'll see exactly how that comes about. Okay? So under gauge transformation, the f mu nu's don't change. But of course, under Lorentz transformation, the f mu nu's change, right? So there are 2 different kinds of transformations you're talking about, a Lorentz transformation and a gauge transformation. The gauge transformation is what happens to the gauge potential. Lorentz transformation is what happens to the Minkowski, the frames that you are using in the tangent spaces of the Minkowski space and so on and so forth, okay? Now, how is this related? This is related to the A's in this fashion, but there's a much more general relationship from which this comes. I told you that in this covariant derivative in here, this thing is like a connection, in fact, okay? So you can define, for example, some quantity A mu. In this case, is equal to minus IE H bar C A mu. There's a reason why we do that, because then the covariant derivative would appear as d mu plus a mu. D mu is equal to partial mu plus script a mu, like that. Okay? Is that right? Yeah. You see, we introduced this quantity because this a mu is supposed to be a physical quantity. So it must, in terms of quantum mechanical operators, it must be a Hermitian operator. And it turns out that the I is required here because the script A is required to be the Lie algebra element, it's required to be anti-Hermitian, and so on and so forth. Okay, this is similar to the fact that when we dealt with those Lie algebra elements in rotations, the infinitesimal generators, those are anti-symmetric. So in the case of quantum mechanics, it has to be anti-Hermitian. Okay. Now we'll leave that aside. And the deal is this. You can write this a mu in here appears like a, classically, appears like a 4 vector. It has 4 components, okay? But what you can do is to do something like that. You can introduce a 1 form that I'm simply going to call a 1 form. And I'm going to write this as a mu dx mu, summed over the dx, sum over mu, okay? Sum over the 4 components in Minkowski space, and so on and so forth. So this is a 1 form in here, okay? No, this is a 1 form in here. Okay. Now, in terms of this 1 form is called a connection in mathematics. In terms of this, I can define what is called a curvature 2 form. I can define a curvature 2 form. In this case, I'm going to define this to be, let me in general give it another name, because this is the symbol that I use in my classical mechanical context as the connection matrix of 1 forms, okay? Which is a 1 form. So I can introduce a 2 form by doing something like this. D omega minus omega exterior product with omega, like that. Okay. Well, in general, omega is a matrix. So in general, omega is a matrix. Well, so in general, if omega is a matrix, now this is not a matrix, okay? Because why? As we mentioned last time, that in quantum mechanics, the fiber is a 1-dimensional space, so that it's not a matrix. It's a 1-by-1 matrix, which is not a matrix. Okay, but in general, omega is a matrix, and I can write omega a matrix element, of which is omega ij. Okay, and I can define this. Now this is a 1 form, so I can define this by introduce something called the Christoffel symbols, like that, where you sum over k. So this is a linear superposition of differentials in here. The ij corresponds to this matrix characterization. In the special case when the fiber space is 1-dimensional, then you don't need these 2 indices in here. That's when we revert to this situation in here, where you just have the 1 mu in here. I'm writing k in here instead. You see what's happening in here? So electrodynamics is a simple situation where the connection form is not a matrix form. It's just a simple 1 form, differential like this. And if it's a simple 1 form, now this wedge in here means both matrix multiplication and the wedge multiplication. So for example, if you want to calculate the ijth element of omega, then you would have d omega ij, and here I would have omega ik wedge omega kj. It's a matrix multiplication now, okay? So when I write it in here, I want you to understand that this wedge in here means both a wedge product, which is, again, like the generalization of a vector cross product, as well as a matrix multiplication like this. But you see, when the thing is not a matrix, then it's just a one-form wedge with a one form. So one forms are anti-symmetric. That term is no longer there in a one-dimensional fiber space. Okay, so in electrodynamics, by the way, when it's not a matrix, the theory is called an abelian theory, an abelian gauge, because the group is just one single element. Okay, not a matrix. Yeah.
The matrix that you're talking about being a scalar would be the omega connection matrices?
These are the connection matrices.
That would be
the things that you saw in classical mechanics.
They would be the ones that make it an abelian when they're on.
No, yeah, when the indices are no longer needed, then it's an abelian because it's not a matrix anymore. Then you can multiply them whichever way you want. Okay. All right. So in electrodynamics, when these things are not matrices, in E and M, omega is just the big omega is just little d little omega. Okay, in electrodynamics. In general, in the non-abelian gauge theories, this is what applies. In mathematics, this is called a curvature two-form. Okay, in physics, this is called what? This is called a field tensor, or two-form corresponding to the field tensor. Let me just try to bring this more into. Okay, let me try to do this differentiation, actually, okay? I'm going to define my two field tensor in this way. This is a two form, so it must appear as linear combinations of, like this, a two form, where sum over I and j in some way, okay? And if you want mu nu. The coefficients will be called f mu nu. When mu and nu are summed over because of the anti-symmetry, you introduce a half factor in here. And this is in fact what the omega is. Okay? And you'll see that the script f is just the same as this non-scripted f with a difference of a minus I factor. Okay? Just the way I did it before. So essentially it's the same. It's the same thing, okay? And if you define the omega like this and set it equal to the omega, but omega now is what? Omega now is just this, right? So it's d of a mu dx mu. You know how to do the exterior derivative of this one form in here, you end up with exactly this. Okay? Do you see how? Let me remind you how to do an exterior derivative, right? Let me go back to here. Let's forget about the Schrödinger equation for the time being. So what we want to do is to do this. And remember this mu is summed over. The general procedure, now when you d a one form, you get a two form. That's automatic, unless the two form is 0, okay? So in general, the d is calculated like this. Partial a mu, introduce another index in it, x nu, dx nu, wedge with the original dx mu like this, where there is supposed to be an unrestricted summation over mu and nu. Okay? Is that okay? Now, let's think simply, okay? Simpler situation where there are two coordinates, let's say, okay? When there are two coordinates, what are the possibilities for mu and nu? 1, 1, 1, 1, 1, 2, 2, 1, 2, 2, 1, and that's it. So the sum consists of 4 terms, okay? Sum consists of 4 terms. And so, All right. So then, now these two are simple, right? I mean, this is just, in fact, these two are equal to 0, okay? Why? Because dx1 wedged with dx1, these those are one form, so they're anti-symmetric, so those don't give anything. That's one of the advantages of using exterior calculus, exterior differentiation, okay? So it automatically keeps track of the tensor indices for you in a certain way, okay? So the only terms remaining are these two, 1, 2, and 2, 1. 1, 2, and 2, 1. Let's write them out, okay? So it's d, let me write this as d, let me write this as d mu, a nu, dx nu, dx mu. Now it's very important when you do this, this one goes before, it has to be before this original one in here. In fact, if there were n of these in here for an n form, then this thing in here involving this extra differential must go before all the others. That's the rule of exterior differentiation. Okay? So how many terms are here? 2 terms, right? It is equal to d, now the first one mu is equal to 2, right? d2 a1 dx2 wedge dx1 plus d1 a2 dx1 wedge dx2. All right, but let's see, but dx2 dx1 is minus dx1 dx2, okay? Be careful in here. Put in a minus sign, and I change, not here, but just here, okay? 1 and 2, like, so these two guys are the same, which means I can factor it out, okay? So what this becomes is d1 a2 minus d2 a1 dx1 wedge dx2. Okay? Now I'm going to show you that that with this guy, if I define this script f mu nu as being equal to d nu a mu minus d nu a mu, and it's very importantly with the factor 1/2 in here, that is going to be equal to that with the factor 1/2. But you see, in that sum in here, the sum is unrestricted, right? In that sum, the way it's written, it means that the sum is unrestricted. So I will have 2 terms, okay? So I will have 1/2 f1 2 dx1 wedge dx2 plus 1/2 f2 1 dx2 wedge dx1. But again, dx2 dx1 is minus of this is minus of dx1 dx2. So this is equal to 1/2 f1 2 minus f2 1 dx1 dx2. So far okay? Now, let's stick in here and see what happens, okay? If I stick in this one in here, the definition of script f, okay? I want to show that it's equal to that, okay? So this is equal to 1/2 d1 a2 minus d2 a1, that's for the first term, minus d2 A1 minus D1 A2 dx1 dx2. Okay, now do you see it? Half d1 a2, half d1 a2, 1 gives you 1 d1 a2, okay? Minus half d2 a1, minus half d2 a1 gives you minus d2 a1. So they're equal to each other. Okay, so that's why the 1/2 factor is stuck in there, to take account of the fact that the differentials themselves, or the coordinates, are anti-symmetric, and also that, but just to take into account that fact, okay? The differentials of the coordinates themselves are anti-symmetric. And the fact that when we write it like this, the sums are unrestricted. The sums are unrestricted, okay? So that's how this comes along. It reveals to you, if this is a curvature, then this is a curvature. Field tensor is a curvature. The field tensor is a geometrical object. It is a curvature corresponding to this particular connection, which is given by the gauge field. The gauge field is a connection, and the curvature is the force. The gauge field is a connection, and the curvature is the force. Okay? There are many other instances, including non-abelian gauge theories, including general relativity, Riemannian geometry, where this kind of relationship holds up. All right, let's take a break here. Okay? So the connection is the gauge field, and the curvature is the force. Okay? I want to just say one more thing about this covariant derivative. Why does it look the way, the covariant derivative was like this. D mu is like d mu plus some quantity a mu, something like that. Okay? And now, let me go back to, for those of you who have taken my classical mechanics course, we introduced on the tangent bundle what is called a connection matrix, and it's defined like this. You introduce a frame field, that means you pick a frame at each and every single point. You introduce the connection matrix by something like this. So J is summed over in here. So we express the covariant derivative to be thought of as some kind of a change, local change of one vector in the frame in terms of all the vectors in the frame. Okay. Naturally, you expect this to be a vector also, and any vector in here should be expressible as a linear combination of all the basis vectors in here like that. But there's no fixed rule except a very few very general ones for the choice of omega ij. Okay. So obviously there are many different kinds of picks, and that can still be called a connection. But normally in the tangent bundle, what we are used to is what's called a Levi-Civita connection. There's a very special pick, and I won't say explicitly what it is right now, except to say that this is the one which is compatible with the metric introduced, and also it satisfies another condition called a torsion-free condition and so on, but I don't want to elaborate on it now. Okay. And now the idea is this, right? So this is like a connection matrix of one forms. So for a 2 by 2 case, this would be like omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. It can be shown quite generally that if the frame is an orthonormal frame, then this matrix is anti-symmetric, which means that these two are equal to 0. And there's only one independent one in here, because this one is going to be equal to negative of that one, the thing being anti-symmetric. Okay? But, of course, you can have bigger dimensions, okay? But in any case, if you do pick orthonormal frames, the connection matrix would be anti-symmetric. But in general, if you don't pick an orthonormal frame, they need not be anti-symmetric, okay? So, but in general, you can write it like this. Now, supposing that I have a vector in here, right? The question is, let's say this is a vector in here. what is the covariant derivative of that vector. All right? So supposing that I write that vector in terms of components, vi, ei, like that. So then the question is, what is the covariant derivative of that vector in here? And the rule is very simple. This is not a vector, it's just a number being a component of a vector in here. So when a D sees this product of two things, you can imagine using the product rule. But when it differentiates this component, it's just an ordinary D, an exterior derivative, not a big D, a little d, okay? So the little d operating on Vi times Ei plus Vi. Now when you have to differentiate the Ei, it has to be the covariant derivative like that. This is a rule, okay? And now, let me write this in terms of using this equation. And so this is B big I Ei plus, let me change this to a J. It doesn't matter, right? Because this is summed over anyway, okay? And so this becomes Vj. And I'm going to write Dej as omega j I Ei, which is the same equation in here, okay? The reason I want to do that is simply I want to factor out the Ei, so this becomes dvi plus Vj omega j I d times Ei, like so, okay? Okay, that's covariant derivative of V, all right? Now let me write the D. Now the V in here is a vector field, so therefore these components are expected to be functions of the coordinates, right? These vector fields of the components are functions of the coordinates. So dvi can be written as dj vi dxj. Is that okay? dvi, differential. You express it in terms of the differentials of the coordinates. All right? Let me write this as a k because my j has been used here already. Plus Vj. My omega ij, this is why I introduced my Christoffel symbols, j, I, k, dxk, like so in general. So this is a differential form in general, so the Christoffel symbols are all functions of the coordinates also. Okay? And so this is gamma j, I, k, dxk. Factor out the dxk. I have this. Now this is a sum, obviously. It's a general differential one form, right? So the sum of something times dx1 plus something times dx2 and so on and so forth. And those somethings are all functions of coordinates. Okay, so it's a general differential one form. Okay, as it has to be, because that's what a covariant derivative will produce for you. Now, if I take you consider this as mathematically, this is said to be a vector in the cotangent space. Okay. And if you consider, with these being the components, this kth component, these are the basis vectors in the so-called dual space, the tangent space, which is the cotangent space. So the dx k's, those are differential forms, are vectors in the cotangent space. And so the kth component would simply be this. That's a kth component. Okay? Now that's beginning to look like this, right? So instead of k, let me write mu. Let me write Greek letters now, okay? Instead of k, let me write mu. So this is said to be the covariant derivative along the muth direction. You can sort of project the covariant derivative along the different directions, according to what these things are, which are coefficients of the dxk's and so on and so forth. Just like you can make a pairing between a cotangent vector and a tangent vector because they are dual spaces, the pairing between them gives a number. Okay? So you take the muth component, it becomes like this. Okay. And now, furthermore, let us then think of the fact that we are dealing with not tangent spaces, but one-dimensional fiber spaces. For one-dimensional fiber spaces, suddenly these indices are no longer relevant, okay? Because it's not a vector anymore. Well, it's a vector, but it's only one component, so to speak. So I don't need an index for that, okay? All right. So you take away those ij's, okay? Is that okay? For 1D fiber spaces, which we're dealing with, in fact, for the quantum mechanical case, okay? See, a quantum mechanical case, the base space is Minkowski space, and the fiber is just a complex line. It's can be considered as a one-dimensional complex vector space, okay? So for 1D fiber space, these are gone. And then the whole thing can be, this operator can be then considered to be operating on this in here. Okay? This is precisely what we have over there. That's a muth component of the covariant derivative, which is along the muth direction, so to speak. Okay? So that operator in the Schrödinger equation, which we have identified as the covariant derivative, is in fact the differential covariant derivative defined very generally, applied to the special case of a one-dimensional fiber space, fiber bundle. Okay, so the base space is four-dimensional. If the base space is treated as Minkowski space, the fiber is a one-dimensional complex space because why? Psi itself can be regarded as an element in that fiber because psi itself is a complex valued function. So whatever value it takes has to be a complex number. Okay. You can even be more restrictive than that because if you consider so-called normalized wave functions, then you can think of it as a complex number of magnitude 1, so to speak. Okay, so it's just of the form e to the I times some real number, like that. Okay. Okay, I just want to draw your attention to the fact that, this thing seemed to have come up very artificially in the Schrödinger equation is in fact very generally a covariant derivative in differential geometry. And whatever it is that occurs in here is the connection, which is the gauge field. In the electromagnetic case, it's proportional to the vector potential, the four-dimensional vector potential. Okay? All right. Now, let's go back to the solution of the Schrödinger equation now. Let me rewrite that again. And we saw that this equation is invariant under this gauge transformation. The gauge transformation consists of two parts, one applied to the gauge potential and the other part applies to the wave function. Where lambda x in this case, is some arbitrary spatially dependent function. Okay. Notice that we are no longer dealing with Minkowski space. The underlying space goes back to three-dimensional Euclidean space. Okay. And associated with this is the gauge transformation of the wave function, which means psi of x has to go to exponential IE over h bar c lambda of x multiplied by psi x. If you make this gauge transformation, then the then the Schrödinger equation becomes is invariant. Now let's ask the following question. Supposing I know the solution to the Schrödinger equation, in this case mu is just 1, 2, 3. Supposing I know the solution to the Schrödinger equation when a is equal to 0, then what is the solution to the Schrödinger equation when a is not equal to 0? Does that make any sense? You have an electron going around originally, and you know its wave function. Now you apply a magnetic field. What's that wave function of the electron going to be? Okay, so that's the physical question. All right, now classic, huh? It's okay to take a guess. Take a punch.
It'd be the same, right? Since like it's gauge invariant.
No, the equation is not gauge invariant. Is gauge invariant, but the solution is not gauge invariant. The equation is gauge invariant. Yeah.
Would it have the phase shift?
Would have the phase shift, but what is that phase shift? That's the question. So it tells you that it's that phase shift, right? In other words, something like this. Okay. Supposing that originally this thing is equal to 0. Okay. Supposing originally this thing is equal to 0. So 0 goes suddenly to d mu lambda x. Okay. So the new a is equal to d mu lambda x. Let me call the new a a. Originally a is equal to 0. So the new a is like this. We are trying to get the new a from the old a by gauge transformation. We saw that it's okay because the equation is invariant under any gauge transformation. Okay, so if in a situation originally where there's no field, okay, suddenly there's a field, you can imagine the introduction of that field to be due to a gauge change on the vector potential. All right? Then it's just a question of, if you look at this condition in here, just a question of figuring out what the lambda is in terms of the newly introduced a. Obviously, what is it? If the gradient of lambda is equal to a, what is lambda? Integral of a over a certain path. Okay? So lambda must be equal to integral of a mu dx mu, which is a line integral. It may depend on the line, okay? So this is integrating from some fixed point, doesn't matter which one, over a certain line. Okay, lambda depends on the path as it turns out. Okay, lambda depends on the path as it turns out in general. Okay. So then, now in the notation in the book, I've done something like this. I reversed the notation, so to speak. I'm saying that the solution to the Schrödinger equation without the a is psi prime. This is without B field, without A, when A is equal to 0. When A is equal to 0. Okay, let me write this out. So the solution for when A is not equal to 0 is then equal to this multiplied by this phase factor in here. Integrated over some path. Okay, so the new solution when there's a non-zero A is given in terms of the old solution. I don't care how that was obtained, okay? Obviously, that depends on the, if you're talking about an electron and hydrogen atom, that old solution would depend on the electrostatic potential. So it's not arbitrary, okay? Whatever it is, let me call it psi prime, okay? But when you introduce the A field, suddenly your solution with a non-zero A field would become like this. Okay? Now this has some serious consequences, which, although it seems to be obvious, was not noticed until the early 1950s by David Bohm and Aharonov, Yakov Aharonov, I guess. So this is called the Bohm-Aharonov effect. Quantum mechanics was, classical electrodynamics was known since the 1860s, and quantum mechanics was kind of non-relativistic, at least, was built up by the 1920s. But this thing in here involving the so-called geometric phase in the form of integral of A dot dl was not discovered until the 1950s. Okay, so there's something quite subtle about it. Okay, but yet it is very important. Let me show you why that is important. What this means is the following. If I have a situation where this integral does depend on the path, right? If I have a situation where this integral does depend on the path, then if my electron takes two different paths, let's say this is point x of 0, this is a point x. And if my electron takes two different paths, let's say the first one is called C1 and the second one is called C2. All right? So the wave function at this point would apparently be different depending on which path the electron went from x of 0 to x, because this integral depends on the path in general. And it does depend on the path in general. That's the whole point. Okay? Now, what makes this thing physically very subtle and physically very strange, in fact, is the following. Supposing I introduce a magnetic field like this. Let's say these are the two paths of the electron. Let's say these paths may not even be very, in the sense of exact classical mechanical paths consisting of lines, that they may be quantum mechanical fuzzy paths in here, like that, okay? Very far apart, let's say. But I introduce a magnetic field in a form that's concentrated at some small location in this region of space enclosed by the two paths. It's entirely possible to do that. I can introduce a solenoid, for example. I can put a solenoid in there. And you know that in the solenoid, the field lines are mostly concentrated inside a solenoid. So outside there's no magnetic field. Outside there's no magnetic field. Okay? But when you try to calculate an A that corresponds to this flux tube in the form of a solenoid, so to speak, you'll see that the A is not 0. The B is 0 over here because the B is concentrated here, but the A is not 0 over. I'll write down the explicit form of that A for you in just a while, so-called Bohm-Aharonov vector potential. Okay? Now then it becomes very funny if you compare the classical and the quantum mechanical situation. Classically, the electrons don't know a thing about the field because where they go, they don't see any fields. Okay? So it would appear that, for either of these two paths, that magnetic field doesn't affect the classical electron. But quantum mechanically, that's a different story entirely, altogether, because, as you see, the A here is not 0. When you do the integral over these two paths, it depends on the path. Okay? It depends on the path. And what this means, you can see it in a slightly different way also. You remember in classical mechanics, when you do the work done by a non-conservative force, it depends on the path, right? So it's a similar situation in here. When a force is conservative, when you do a loop integral, what is the line integral of the force? 0, right? When the force is non-conservative, the force depends on the path, so that the loop integral is not equal to 0. Such a case is obviously true for the frictional force, any type of frictional force whatsoever. Okay? Energy is not conserved. So now first of all, let me try to do a loop integral then. Try to do a loop integral of A dot dl. For example, I may consider this loop going like so. This loop. Okay? Let's say that the region enclosed by the loop is D. So in fact, I'm doing the line integral over the boundary of D, and that's the notation we have been using, right? Let's use Stokes' theorem. What is this equal to? dA over D, okay, over D. But what is del cross A? B. And what is that? The flux. As long as there's some magnetic field here, the flux, the magnetic flux is not equal to 0. We can even cook it up so that that flux is constant. Not 0, okay? Flux tube. So the deal is, an electron, let's say wave function you consider here, and if you make it progress around the loop, it gains a non-zero or a non-zero geometric phase. Okay, it gains something in here. Okay, this is called a geometric phase. That's gained by the quantum mechanical system as it goes around the loop in here. Experimentally, this is can be actually verifiable, and it has been verified many, many times, because you somehow has to set up a flux tube in here, and then you propagate an electron around 2 different paths, okay, and try to observe the interference of the 2 electron beams over here, okay. There's an interference. These 2 guys are not the same, so there's an interference pattern that can be observed on the receiving point, quantum mechanically, okay? That's called the Bohm-Aharonov effect, or the Aharonov-Bohm effect. I don't know, I forgot which name goes first. Most people call it the Aharonov-Bohm simply because it's AB, okay? There's another aspect of AB also. In classical mechanics, B is more important than A, because B is the field, so the field strength is considered more basic, more fundamental. A can be subjected to any sort of gauge changes, but yielding the same B, okay? So A in classical mechanics, classical electrodynamics is viewed as secondary, okay? In fact, people consider it a nuisance, because then or sometimes a nuisance, sometimes an advantage, depends on what you want to do with it, okay? So then this is a problem of different gauges that people introduce to solve different problems and so on and so forth. But in quantum mechanics, you see, A is more important because the quantity of importance is A dot dl is not at all the B, okay? A comes before the B. I don't know why the letters were chosen in this way, but I guess when people chose the symbol A for the vector potential and the symbol B for the magnetic field, they had some foresight, because in fact A is more important than B. Okay, only that in 200 years ago they didn't know about this. Yeah.
So we're using different vector potentials, different A's. Initially A was 0, and then we introduced some B, which gives us some A.
We introduce physically you can think of it this way. Okay. But then locally you can always transform the A away by a gauge transformation. That's why we can use this kind of a procedure in here like that. Okay.
I was just wondering what sort of gauge are we using in this case in order to make it so that A is the same as when it was initially?
We are using the gauge such that any gauge, in fact, whatsoever, where del cross this is equal to B, okay? So the B is whatever it is, okay? But since, in a sense, the B is secondary now. The B is secondary now, quantum mechanically, okay? Because B is not relevant. Everywhere around this loop, B is equal to 0. But the A is more important now, okay? Because of the emergence of A dot dl. Yeah?
Can we think of the phase factor as a vector, a tangent vector on some line?
Yeah, you can think of a phase factor as a vector in the fiber, okay? So that a wave function is like a vector field, okay? There's a complex number at each point in the base space, a complex valued function, okay? That's why we say that the fiber for the non-relativistic quantum mechanics, for the scalar wave function, is a line bundle where the fiber is a line, so to speak, one-dimensional complex space.
So there's a way we could parallelly translate on that.
Yes, and that's precisely the set the covariant derivative equal to 0. All these things are tied together. In fact, you see, this is intimately connected to the parallel translation. What was parallel translation? The parallel translation was d psi is equal to 0, right? And so we wrote it in terms of this d mu minus I e h bar a mu psi is equal to 0. What's the solution of this? It's precisely something like that, okay? Psi is equal to some psi naught times e to the minus plus I e over h bar. A dot dl integral, okay? Right? So this form of the solution is in fact the solution produced by the parallel translation of psi. So when you parallelly translate psi, you automatically produce the solution for the Schrödinger equation with the presence of a gauge potential. That's another reason why the parallel translation is important in this case.
So would the fiber be isomorphic to like S1?
No. The group is S1. The group is isomorphic. The gauge group is isomorphic to S1 because the gauge group is U1. Okay. U1 is U1 is isomorphically is homeomorphic to the one sphere, so to speak. Okay, because U1, after all, what is U1? U1 is e to the I theta. A particular element is e to the I theta. Okay, the theta can be anything. Okay, and so when you let theta go from 0 to 2 pi, it's like e to the I theta is like the circle on the complex plane. Okay, so U1 is the group that transforms the fiber elements. The fiber is let's say this is the base space, right? Whatever it is, okay, Minkowski space or whatever. What is meant by wave function? Wave function is meant by choosing a particular complex number at some position, right? So it's expressed as psi x, right? So for every x, I have some complex number, right? So let's say this is a complex, this is a space of complex numbers. Huh? One point in here is some complex number, okay? So at a base point in here, I choose some complex number. At another base point, I choose another complex number. At another base point, I choose another complex number. This is actually what is called a section of the bundle, which is just like a vector field because you choose a value at every point on the base space, okay? So the idea is, now the gauge in here corresponds, the different choices of gauge in here, in fact, corresponds to where you pick the origin of this coordinate system, so to speak. Okay? So for example, in complex space, you could still take the number plus 1 to be the basis vector, okay? So that any number in here can just be written as some complex number times 1, like that. So it's a one-dimensional complex space because there's just one complex component in here. That's all, okay? But you can choose the basis to be this one. You can equally choose the basis, the unit basis, to be any vector here. All right. Well, but what's the relationship between these two complex numbers? multiplied by e to the I theta for some theta. So different choices of base vectors in this case corresponds to the multiplication by e to the I theta. Okay, so those are the group elements, so to speak. That's a one-by-one group. That's a one-by-one matrix group whose element is e to the I theta. That connects the different basis vectors in here. So the group is U1. The gauge group is U1. Okay, gauge group is U1, and different choices of gauge just corresponds to here. In fact, this is theta, and you don't write it as lambda, you write it theta. Okay. What that means is that when you come to think about it, this is just an angle in here. You can look at this as an angle, okay? And if you go from one basis to another basis, you just multiply it by some angle. But since it depends on x, that means you're choosing a different basis at every different point. Okay, you're choosing a different basis at every different point. That's exactly what we did when we had the tangent bundle. We choose a different frame at every point. That's called the gauge transformation. That's a local gauge change because the gauge, the matrix element in here depends on position, okay? As opposed to some global gauge change where you do the same angle change at every single point in space. So gauge field theories are required to have this local gauge invariance. That's a very important kind of symmetry. Yeah?
So can we consider the path as like circles on an S2 and like the great circle would be the G?
No, we're not talking about that at all now, okay? There's no S2 right here. The abstract setup is that you have some base space and you have some fiber. The fiber can be any sort of vector space, okay? In this case, real or complex. In this case, the vector space is a one-dimensional complex vector space. That's a fiber. The fibers are all isomorphic to each other because they're just the line of complex numbers, okay? One-dimensional space of complex, and they're all isomorphic to each other, okay? And picking different gauges in this case just amounts to picking different points as points of origin, so to speak, for you to reckon what the angle is, okay? You have to think about it a little bit more abstractly, all right? Like so. Okay, I think I want to stop here, and next time we come back, we'll continue, and I'll write down explicitly, well, actually you can read about it yourself, explicitly the form of the Bohm-Aharonov potential, and you can actually, in fact, let me just take a couple of minutes to write it down, and you can go home and verify it yourself, okay? I think we'll still be in good shape. So you consider that we have shown this picture in the book in here. Just look at this picture. And let's say this is a point of the solenoid, and I have an electron going two paths. I take this to be the origin of some coordinate system. Let's say we take the loop to be on the xy plane so that the z-axis is pointed out this way. Okay, so this is x, this is y. And I can write my vector. Let me introduce a three-vector potential like this. The total magnetic flux is phi, which is a constant, okay? Minus y over 2 pi r square phi. That's the x component. The y component is x times the same constant phi divided by 2 pi r square also. And there's no third component for the vector potential. So in fact, you can actually try to draw a picture of what this A field looks like. It's just like it's concentric circles. It's not too hard to see that. Okay, the A field is entirely along the xy plane. You can prove that it is just concentric circles. So the A field looks like this. So wherever the electron is, there is an A field where it is, especially, in particular at these points where it's traveling, there's an A field. Now, you can calculate pretty easily that del cross A dot dA integrated over this region, which is bounded by that path, is equal to phi. You can calculate that. Go home and calculate that. Okay, this is an exercise. Furthermore, you can calculate, if you take these three components, x, y, z components, r squared, of course, is just x squared plus y squared, right? That's trivial. Okay, r squared is just x squared plus. You can use the ordinary formula for the calculation of the curl and show that the curl of this is 0 everywhere except for the origin. Okay. So here, in particular, everywhere except this point in here, the B field is equal to 0 because the curl of this A field is equal to 0. So it satisfies this Bohm-Aharonov condition, so to speak. Go home and try to do that and convince yourself of everything that I have just said. The curl of this field is 0 everywhere except at the origin. And now, the loop integral, any loop of any shape which doesn't cross the origin, as long as it encloses the origin, the flux integral or the loop integral of A dot dl is equal to phi. It doesn't depend on the shape. Now, it's most easy to calculate it when you choose a circular shape because the A is exactly tangent to any of these circles, so it's very easy to calculate the A dot dl for this particular case. But it is not too hard to argue that the loop integral of A dot dl for this field, for any loop whatsoever, as long as it encloses the origin, is equal to phi. Go home and show that also. Show three things. The curl of this is equal to 0 everywhere except at the origin. The loop integral of A dot dl over a circle with the center of the circle at the origin is equal to big phi. The loop integral of any loop enclosing the circle is also equal to phi. So the loop integral doesn't, as long as that loop encloses the origin, it doesn't depend on the shape of the loop. A very interesting thing.
So it's kind of like Cauchy integral.
Yeah, it is kind of like Cauchy integral, yeah.
What was the second thing you wanted to show?
That the loop integral over the circle, some circle, is equal to phi. And from that you argue that the loop integral over any loop, as long as that loop encloses the origin, is also equal to phi. Is equal to, in other words, the loop integral does not depend on the shape of the loop as long as the loop encloses the circle. Go home and show these things. Okay, that's quick at this point. After that, you will understand exactly what we are talking about when we discuss the Aharonov Bohm effect.